right, welcome back to the technology track. We're so excited to welcome a great lineup of speakers for this block. Our next speaker is Leanne Friedrich. She's a postdoc at the National Institute of Standards and Technology. She uses simulations and in situ imaging experiments to identify strategies to improve print quality and embedded 3D printing of soft materials. She received her BS in Material Science and Engineering from Northwestern University in 2015 and her PhD in Materials from University of California, Santa Barbara in 2020. Her dissertation, titled Tailored Composite Microstructures via Direct Ink Writing and Acoustophoresis, don't know what that word is, explored strategies to improve print quality in a novel 3D printing technique which used sound waves to manipulate the microstructure of polymer matrix composites. Welcome, Leanne. Thank you so much for being here, and I'll leave the stage to you.
Great, thank you. So today what I want to talk about is how we can leverage material science to accelerate embedded 3D bioprinting. So my name is Leanne Friedrich, and I'm a postdoc at NIST. So I want to start with an overview of some of the common polymer 3D printing techniques so we can situate embedded 3D printing in terms of the material space and how it fills out the material space for polymer 3D printing. So there's fused deposition modeling, which is the most common consumer type. There's vat photopolymerization, and then there's direct ink writing, which is starting to emerge more in R&D spaces. So fused deposition modeling, or FDM, is a nice technique for consumers because it is limited to thermoplastics. So the polymer space can be split into thermoplastics, where you can heat them up and cool them down and still maintain the same properties. So things like ABS, PLA, polycarbonate, those are thermoplastics. The other segment of polymers is thermosets. So those have irreversible bonds. You cannot heat those up and cool them down and reform them. So things like epoxies and polyurethanes and silicones. So the way that fused deposition modeling works is you have this polymer filament that has to be a thermoplastic because you're feeding it through a heated nozzle to make it formable, and then you write out the continuous filament onto a substrate and build up your part layer by layer. So because it's limited to thermoplastics, we need other techniques to fill out that material space and make thermosets printable. So one of the ways you can print those is using vat photopolymerization or stereolithography additive manufacturing. So the way this works is you have a vat that is full of a photopolymer resin. So that means that when you shine a light on it of a certain wavelength, that'll cure it and turn it into a solid. So you submerge your stage into that bath and write out your part layer by layer again. So that takes care of photopolymers, things like epoxides and acrylates, which are a subset of thermosets. But we're still missing a lot of the thermoset space, so we need another technique, which is direct ink writing. So the way that direct ink writing works is you have a reservoir that's full of your ink, and you extrude it through a nozzle and write out continuous filaments onto a substrate. And you can use a variety of extrusion methods. You could use pneumatic extrusion, so you have an air pressure that is pushing this fluid out of the nozzle. You could use a piston, you could use a screw. And then there are a variety of curing techniques. So once your part is written out onto the substrate, you can cure it using a variety of techniques. If it's something like alginate, then you could submerge your part into a calcium bath for ionic cross-linking. If you have certain biopolymers, then you could use enzymatic cross-linking to turn that part into a solid. You could, again, use UV radiation. So all these photopolymers are then going to be printable using direct ink writing. And then there's thermal curing. So if you have something like an epoxy, you could write out your part and then heat it up to cure it. So because you have this big range of curing techniques that are available to you, direct ink writing really opens up the material space to include a lot of those thermosets, as well as some other types of materials. You can print ceramic slurries and ceramic matrix composites using this technique because you have that variety of curing techniques. So people have been able to print things like rubber, ceramic matrix composites, polymer matrix composites, and hydrogels using direct ink writing. Now, the limitation with direct ink writing is that you can only print inks that have a certain range of rheological behavior. So they have to flow in a certain way. So what we're looking at here is a plot of a variety of different materials where we've plotted the shear modulus, the storage modulus, and the loss modulus as a function of the shear stress imposed on that ink. So what this means is if G prime is greater than G double prime, then that material is going to behave like a solid. And if G double prime is greater than G prime, that means that the material is going to behave like a liquid. So if we look at low shear stresses, you can see that G prime is greater than G double prime. So it's going to behave like a solid there. And that's going to reflect the behavior of the material after it's printed onto the substrate. Inside of the nozzle, we're going to be at high shear stresses, and you can see that G double prime is greater than G prime, so this material is going to behave like a liquid. And then in between that solid-like to liquid-like transition, there is a yield stress. So that's the stress at which this material stops behaving like an elastic solid, starts to behave like a liquid. So that yield stress needs to be high enough that the material won't just collapse under its own weight. It won't just flow onto the substrate if you bump the stage or move the stage around. Another way that you can look at the rheology of these materials is using viscosity curves. So we're looking at the viscosity as a function of shear strain rate here. And what you can see is that these are shear thinning materials. So as you increase the shear rate, you decrease the viscosity. So what that means is if you print at high speeds, that'll decrease the viscosity of the ink. And that means you can still get it out of the nozzle without using exceptionally high pressures. At slow speeds, such as when the ink has just come out of the nozzle, it's going to become more viscous and it'll resist flow and be able to hold its form. So among these inks that are plotted here, at the top of the plot where we have these dark lines, those inks are going to be printable because they have a high enough yield stress that they will not just collapse under their own weight. However, at the low end of this plot, and these light blue inks, these are not viscous enough, they're not shear thinning enough, they don't have a high enough yield stress to be printable using direct ink writing. So that's where embedded 3D printing really becomes useful. So the way that this works is you have a print bath that is full of a support fluid. Usually that fluid will have a yield stress and it'll be shear thinning just like those materials that I talked about in the last slide. So things like carbopol hydrogels or laponite hydrogels. Those will be good support baths. So you embed your nozzle into that bath and then write out continuous filaments for embedded direct ink writing, or you could print out droplets for embedded droplet printing. So because these materials have a yield stress, they'll behave like a liquid when the nozzle is moving through them, and that'll allow the nozzles to move. But they'll behave like a solid after the nozzle has left, so they'll hold the form of whatever you printed. So this means that we can expand the available material space into low viscosity materials, and we can print thin-walled structures and delicate structures because we don't have to worry as much about the properties of the ink when you have that extra support available to you. So after you're done printing, you can remove these parts from the bath either by scooping them out or using dissolution in a buffer. So what this means is those blue inks, those low viscosity inks, are now going to be printable as long as we use a support bath. So people have been able to print a wide variety of materials using this technique before, and it's been particularly useful for bioprinting. So you might have seen this paper a couple of years ago where they printed a heart, which actually included human heart cells, as well as some extracellular matrix. So you can print these cellularized constructs and actually use the bath to support the growth of that construct by introducing nutrients that'll feed the cells that will allow this construct to, the cells to proliferate. People have also been able to print cell-only inks. So instead of having all these biopolymers available that'll scaffold the ink, they can print just cells, and those cells have been able to grow and develop tissues. And then you can also print functional materials. So things like electrically conductive hydrogels, things that are at a low viscosity, where you've already tailored your ink to a certain functional property like electrical conductivity. You can still print that ink by using a support bath because that support bath takes care of the rheology aspect. So what I want to talk about in this talk is how you choose a support bath for embedded 3D printing. Usually you already have an ink in mind that is going to support your cells or serve some functional purpose. And so how do you choose a bath that is appropriate for that ink? And there are two considerations that you need to take into account. There's rheology and there's surface tension. So in this talk, I'm going to talk about model materials, which are relevant to bioprinting, but have certain rheological properties that are going to tell us about how the rheology is important. So I'm going to talk about how defects can occur in individual filaments in embedded 3D printing. So this is a simulated filament. You can see that blue column is the ink that's inside of the nozzle, and you have a filament that's coming out of the nozzle. If you look at the cross section of that filament, it's not circular like the nozzle is. It actually has a sort of fin shape, so it narrows towards the top and towards a point. So I'm going to express that cross section in terms of the aspect ratio, the height over width. I'm also going to look at the length of these filaments. So if I ask the printer for a 10 millimeter filament, I want a 10 millimeter filament. Oftentimes, if there are defects, these filaments will end up a little shorter than you intended them to be, and that's going to cause a lot of problems in terms of the shape fidelity of the part. So we're looking for a length that's exactly as long as we asked for. We used two methods to identify these sources of defects. We used simulations and experiments. So these simulations were done in OpenFOAM, which is a computational fluid dynamics solver. So we extruded, imposed a pressure of ink onto a static nozzle, and then had a moving bath moving past it, and so that would extrude a single filament. We also used in situ imaging experiments. So again, we have a static nozzle and a moving bath, but this time we have a camera looking at the tip of the nozzle so that we can see what's happening as we're printing. And then once the print is over, we can remove the nozzle and go back and take images of our print. So for these experiments, we printed straight lines where we looked at the lines head-on to identify their cross-sectional shape and printed them out from the side to look at their lengths. So first, let's talk about how rheology influences filament defects. In this section, we're going to have no surface tension, and our ink speeds will be set equal to the stage speeds. So I'm going to investigate a variety of different rheological behaviors. So one type of material that has been printed is the Newtonian material. So usually in these papers where they're using Newtonian materials, they'll have some sort of stabilizer at the interface. So they'll be printing oil into water, but they'll have a particle that stabilizes the interface so that the material doesn't break up into droplets. In our simulation, we use Newtonian fluids in order to identify what is the effect of viscous dissipation on this process. We don't want to have to worry about yielding or elasticity or anything else, just viscous dissipation. We also simulated Herschel-Bulkley fluids. So these are the fluids that are like the fluids that I talked about in the beginning, where they're going to behave like a solid up until a yield stress, at which point they're going to behave like a shear thinning liquid. So for these simulated fluids, all of the behavior in the shear thinning region is going to be the same. These are all going to have the same viscosity above yield. But below yield, they have different viscosities, which I call the plateau viscosity. So that is going to extract just the effect of what the unyielded properties of the materials do to the structure of the filament. And then finally, for our experimental fluids, we're going to look at a variety of fluids, but generally they follow the same pattern, where they're shear thinning, but as you increase the amount of rheological modifier in that material, you're going to shift this entire shear thinning curve upwards, so increase its viscosity. So what I'm showing you here is laponite and water. So laponite is a fumed silicate, and it'll form these structures that will give it a yield stress and give it shear thinning properties. So first, let's look at our Newtonian simulated materials. Here we're going to be looking at cross sections, and ideally these cross sections are going to be circular. If they are too tall and narrow, then you might end up with anisotropy in your final part, because you'll end up with a different resolution in your XY direction than your Z direction. We're also going to be looking at a circular shape because if there's any sort of sharp edges on these filaments, That could lead to porosity in the final part, or it could lead to surface roughness, both of which would be problematic. So for these Newtonian fluids, remember this viscosity is going to be constant with strain rate. And so here, what you can see is if you look down these diagonals, you can see that the cross-sectional shape is the same. So what that tells us is that the viscosity ratio is what's really controlling the filament shape here. So that's the ink viscosity divided by the support viscosity. Now let's look at Herschel-Bulkley fluids. So here we're going to have a constant plateau viscosity up until yield stress, at which point the viscosity will drop off towards shear thinning behavior. So here what you can see is if you go to a high plateau viscosity for both the ink and the support, beyond a certain point, all of the cross-sections are the same. So all of these Herschel-Bulkley inks behave similarly, and all the Herschel-Bulkley supports behave similarly. And remember, the way that we set these viscosity curves, the viscosity above yield is the same for all of these. So we can identify why that happens by looking at slices of our simulation. So here I've sliced through the bath, and the color is indicating the viscosity of the fluid. So in the center of these plots, you can see there's this sort of white outline. That's the outline of the filament. So inside the filament, the viscosity is about 1 to 10 Pascal seconds for all of these. And then there's a yielded zone outside of the filament where the support is at about 1 to 10 Pascal seconds. And then outside of that yielded zone, all of these supports are at a different viscosity, which is their plateau viscosity. So because we have the same viscosities within the yielded zone locally, that means we have the same local viscosity ratio for all of these plots, and that's why we get the same filament shape. So we learned here that the local viscosity ratio is what controls the filament shape. So now let's look at our experimental fluids. So here, our local viscosities are going to change, and they're going to increase as we increase the concentration of lapinite in the material. So here we're printing lapinated water into lapinated water, but our ink has a little bit of dye, so we can see contrast. So if you look at the bottom right corner of this plot, you can see that as we go to high ink viscosities and low support viscosities, we get circular filaments. If we go towards the top left corner of this plot, where we have low ink viscosities and high support viscosities, we get very tall and narrow filaments. And these filaments also get sort of sharp edges at the top and at the bottom of the sides. So in order to compare this to the simulations, remember the simulations taught us that the local viscosity ratio controls the filament shape. So let's identify the local viscosity ratio. You can get that by taking your print speeds, so the speed of ink moving through the nozzle and the speed of the stage moving underneath the nozzle. Divide that by the dimensions of the nozzle, and that'll give you your shear rate. Plug that in, you can get your local viscosity. So in the top left corner, you can see those dotted lines. Those are our local shear rates. So that's how we get our local viscosity. So here, what you can see is that as you increase your viscosity ratio, you decrease the cross-section height over width. That occurs in both our simulations and our experiments. And there's pretty good agreement as we go to higher viscosity ratios. So what this tells us is that if the support is more viscous than the ink, it just ends up squeezing the filament vertically and creating these very tall and narrow aspect ratios. Another thing that we can note here is that you need to go to a viscosity ratio of greater than 1 in order to get a circular cross-section. So the ink needs to be a little bit more viscous than the support to get to this ideal circle. Okay, next let's look at how surface tension influences filament defects. So we're going to introduce some oil-based inks that we're going to print into our water-based support. So here we're simulating some filaments that are being extruded into a bath at a surface tension of 40 millijoules per meter squared, which is about what you would expect for oil and water. So you can see again, as you look down the diagonals at high viscosities, the viscosity ratio is what is controlling the filament shape here. But as you start to go towards lower support viscosities, we see a little bit of deviation, and we see filaments breaking up into droplets or just clinging to the nozzle as a singular droplet. If we compare that to our experiments, Here, these experiments are covering a smaller region of this viscosity map in terms of the local viscosities, but you can see we get the same pattern, where at low support viscosities, we get filaments that break up into droplets or start to go towards a spherical shape. And if the ink viscosity is low, you get filaments that break up into droplets. If the ink viscosity is high, you get a full filament that then shrinks back towards a spherical shape. If we go to high support viscosities, we suppress that breakup and we still get continuous filaments. However, they are pinched. So if you look at the cross-section of these filaments, they're a little bit taller and narrower than the circular cross-section that we're looking for. So that pinching is the same sort of pinching that we saw with our water-based inks, where we have tall and narrow filaments that occur at high support viscosities. So in order to map these oil-based inks onto some sort of constitutive relationship that tells us how we can balance all of our properties, we can use the capillary number. So that's the speed of the ink times the viscosity of the support divided by the surface tension. So that capillary number is telling us how we need to balance the viscous dissipation in this system against surface tension. So here you can see that as we increase the capillary number, we get a taller cross-section height over width. And so that's telling us that we get more pinching as we go to those higher capillary numbers. So that's less than ideal. However, these aspect ratios are not as tall and narrow as the water-based inks that we saw. And I'll also note that when you have these oil-based inks, you don't get any of the sharp edges or flat bottoms that you see in these water-based inks. So we always have rounder filaments, which is going to be an improvement for our surface roughness. If we plot the length of these filaments as a function of capillary number, you can see that we get longer filaments closer to the ideal length as we increase the capillary number. And so in order to suppress that shrinkage that I talked about at low ink viscosities and low support viscosities, we need to use a high capillary number system. So as a trade-off, we'll have to be able to deal with a little bit more pinching and a little bit taller aspect ratios than ideal. Another advantage of using an oil-based ink in a water-based support, or vice versa, is that you can suppress swelling. So these inks are made out of polyethylene glycol diacrylate with water and dye, as well as some fumed silica as our rheological modifier. And you can see here that these filaments are much, much larger than they are intended to be. And the reason why that happens is because these inks are about 60% water, and the support is about 97% water. So you get an osmotic pressure that drives water from the support into the ink and causes the filament to swell. And that's going to cause a lot of problems because as you're printing your part, the filaments that you've already printed are going to be swelling, and you're going to be printing new filament that is smaller. And so you get a lot of geometric inaccuracies, and you could end up with problems with fusion. So suppressing that swelling is really important. So to summarize, embedded 3D printing, or embedded direct ink writing, is a really useful tool for printing low viscosity materials, and really has a lot of promise in the bioprinting space because bioprinted materials or biomaterials tend to be low viscosity and have specific properties that you're looking for when you're printing cells and things like that. If you're choosing a support for embedded 3D printing, you need to make sure your local support viscosity is slightly lower than your local ink viscosity near the filament. And finally, a non-zero surface tension can be useful if you want to produce rounder filaments and suppress surface roughness and swelling, but you need to choose a capillary number that is high enough to suppress shrinkage. So you can use your support viscosity and you can use your surface tension to make sure that you don't get filaments rupturing or shrinking back towards a spherical shape. So with that, I'd like to thank you all for listening, and I'd be happy to take any questions.
All right, thank you so much. We have tons of questions, which is great. As a reminder, if you are wanting to submit a question, please use the Q&A tab which is to the right of the chat and participants tab. All right, so the top question right now is, could you please share the presentation with us?
Yeah, if you want to see the presentation again, you can email me, leanne.friedrich@nist.gov, which should be in my profile.
It's always a good question. That means there's lots of interest. That one got voted up a lot. Also, just so you know, these presentations are recorded and there will be information on how to access that. All right, next question is, when will we be able to print brains?
Yeah, I think we're a long way off from brains. Things like ears, things that are mostly cartilage, we are pretty close to printing because they're so simple. Things like livers and kidneys and hearts, those have very complex vasculatures. You have to get all of these really tiny capillaries in there. And so it's going to take, and there's a lot of material variation. So it's going to take a lot longer to get there. So brains, I would say decades off.
All right. What are your thoughts on the applications of different 3D printing processes like FDM, SLA, binder jetting, DED on bioprinting? How could each of those be utilized?
Yeah, there's definitely a range of opportunities for that. Even things like metal powder bed processes are useful for bioprinting if you want to do like a bone scaffold. Yeah, FDM, I would see probably fewer applications for internal use. Things like prosthetics you can already do though, which we saw earlier today. And that goes for SLA as well. Yeah, I mean, for both of those, it's the material space limitation. So a lot of the biomaterials, they're not going to be thermoplastics. They might not necessarily be photopolymers because a lot of them have toxicity problems. But I wouldn't say that this is the only viable method for bioprinting. It's just very useful for soft materials.
Awesome. What limits the maximum support matrix or something else?
Yeah, for maximum print speed, you're going to end up with the same limitation that you have with conventional direct ink writing, which is that there's going to be some maximum pressure that you can get to extrude your material out of the nozzle. Because you can use lower viscosity materials here, you can probably get to a little bit higher speeds than conventional direct ink writing because your viscosities just aren't as high. But if you want to do bioprinting with very high resolution, then you're going to get to a smaller nozzle, so that limits your pressure. So a lot of the limitation comes down to extrusion pressures. There are also problems when you choose certain print speeds. If you choose a certain ratio of support speed to ink speed, then you might end up with your filaments breaking up into droplets. So that has to be finely tuned. But I think you can get up to pretty high speeds theoretically. I just haven't looked at the maximum yet.
All right. This one's kind of similar. Are the different printing speeds predefined by the manufacturer of the bioprinter?
Yeah, I mean, the printer that I have, it's a CNC mill, which we removed the CNC from and then added a pressure extruder. So that's me defined.
All right. One last one. Can the vibrations from the 3D printer's head movements shift the material around while printing, or is the viscosity high enough for everything to stay in place?
Yeah, I think that's definitely a good question, because there's a potential that you could, if you're coming around a corner at a very high speed, that could induce a vibration that would be high enough shear rate to actually disturb the entire bath, and then you'll lose that solid-like behavior. So that is something that you have to take into account when you're choosing your print speeds and choosing your path design. Making sure you don't have those fast turns, which cause a lot of problems in conventional direct ink writing and also cause problems here.
Awesome. Well, thank you so much for such an interesting talk. I had no idea that there was so much physics in this technology, but I was just really, really excited to see that. So thank you again. And we will set up our next speaker. So